Hello everyone, I'm Farzad Zafarani from Purdue University, and today I'm going to talk about differentially private naive-based classifier using smooth sensitivity. This is a joint work with Clifton from Purdue University. So this is the outline of my talk. At first, I'm giving you some motivation about the problem. Then I go over a little bit background on the naive-based classifier, differential privacy, and finally smooth sensitivity. Then we discuss a differentially private naive-based classifier using smooth sensitivity. And finally, I present some experimental results. So a model generated by a machine learning algorithm when trained on a dataset can reveal sensitive information. So consider the scenario that we have a training dataset. Of course, we cannot reveal that as a part of the privacy protection. And the hope is to train a machine learning model that goes through a lot of training, and we could potentially publish and not reveal the sensitive data, whose privacy must be preserved. So the hope is that the model can be shared and get published. Well, the problem is that the machine learning model captures a lot of information from the input, and by doing that, the model contains a lot of information about the input. So intuitively, what's happening here is that the model reflects very interesting details about the input. And that is the reason why membership attacks and model inversion attacks are actually quite powerful in this case, because the information is actually captured in the model. So there are a series of recent works that use differential privacy to protect users' data within a machine learning model. Some examples are differentially private decision trees, SVM, deep neural networks, logistic regression, naive-based classifier. And naive-based classifier is a popular machine learning algorithm used as a baseline for many tasks. So let's just go over the definition of the naive-based classifier. So given a training set of examples with a corresponding labels, the task is to assign a new class C map to an unseen instance X. So the learning task would be that for each instance X consists of M features, assign a conditional probability of P of Cj given X for each K possible classes. And the CMAP is assigned to be the maximum conditional probability Cj given X for all J's. Then we use the Bayes theorem to rewrite the above formula, and finally the naive Bayes makes this simplifying assumption that the attribute values are conditionally independent given the target value. Therefore, we get C of NB to be argmax of probability of Cj times the product of all conditional probability of Xi given Cj for all i's. Okay, next we go to the definition of differential privacy. So differential privacy was first introduced in 2006 by Dwork, McSherry, Nassim, and Smith. We give the definition from a follow-on paper by Dwork. So epsilon differential privacy, which is a mapping between the database space and the outcome space, says that for any two neighboring data sets, meaning within L1 distance in their histogram representation, and any subset of mechanism that we might be interested, the probability that our algorithm maps the first database into the outcome space is multiplicatively very close to the probability that our algorithm maps the second database into that outcome space. So Another concept to discuss is the notion of sensitivity. The sensitivity of a function f is defined as how much the output of f may change between neighboring database x and y. So there are two types of sensitivity. One is global sensitivity, which for a function f with respect to L1 metric is the maximum absolute difference between the outcome of f for all pairs of neighboring databases. The other one is called local sensitivity, which is defined for a given database X, and we only look at the neighbors of X and report the maximum absolute difference between f of X and f of Y for all neighbors of X denoted by Y. So the thing to note here is that adding noise proportional to local sensitivity tells you something about the data set. So it doesn't really end up giving you differential privacy. So Nassim et al. Defined a smooth bound that addressed this by not looking at the neighbors of the current data set, but also their neighbors. So they defined the smooth bound, which is for a beta greater than 0, a function s is a beta smooth upper bound on the local sensitivity of f if it satisfies the following two requirements. First, it is greater than or equal to the local sensitivity, and second, it is a smooth function. And we have demonstrated that in the right-hand side figure. So next is the definition of smooth sensitivity by Nassim et al. For a beta greater than 0, the beta smooth sensitivity of f is defined as the following equation. And in their paper, they have discussed how to compute the smooth sensitivity of a function f. So the smooth sensitivity of a function f at distance k is as follows. And we can express the smooth sensitivity of f in terms of a of k. So next we discussed the differentially private naive-based classifier using smooth sensitivity. So a standard approach for fitting a machine learning model to a numerical attribute is to assume that the underlying distribution is Gaussian. We assume that the numerical features values are bounded and compute the smooth sensitivity for estimating the parameters of the truncated normal distribution. We also only train using a subset of the data. The way this subset is defined enables us a smooth bound. So we give the definition for the trim sample. It's just let x denote the sample in a sorted order and let m be a trimming parameter. The trim sequence of sample x is defined to be xn plus 1 till xn minus m. So in other words, we are drawing a window of size n minus 2m on the data. Okay, so in the following theorem, we say how we can compute the smooth sensitivity of the mean. Given a list of n bounded real numbers v from x1 to xn in the range of the interval L to U, the smooth sensitivity of the mean can be computed. And the high-level proof idea is that we either move the k leftmost elements to U or move the k rightmost elements to L. Okay, next we discuss how we can compute the smooth sensitivity of the variance. We first define the k maximal variance subset. So given a set of v of n real numbers in the ascending order and an integer k, a subset Q is called a k maximal variance subset of V if the size of Q is K, and the variance of Q would be larger than any other subset of the same size K of V. And we have this theorem that given a list of n-bounded real numbers, V, in the range of interval L to U, and an integer K, the K maximal variance subset can be computed in O of n squared. Okay, and we provide the following corollary. It says that given a list of n-bounded real numbers in the range L to U and an integer K, the K maximal variance subset can be achieved by removing n minus K consecutive elements in V. Okay, next we define how the smooth sensitivity of the variance can be computed. The following theorem says that given a list of n-bounded real numbers, V, in the range of interval L to U, the smooth sensitivity of the variance, V, can be computed in O of n squared. So the high-level proof idea is that we iterate through K consecutive elements in a data set. We move the first T elements to L and write K minus T elements to U. And we move one last element to its extreme case, L, U, or mu of the window. Or we move K tail elements in the dataset. We move T leftmost elements and K minus T rightmost elements to the mean of the remaining window. And we move one last element to its extreme case, L, U, or mu of the window. Okay, so we have included our algorithm pseudocode on the right side. So the way we distribute the privacy budget, or epsilon, between numerical attributes and categorical attributes is with a ratio of 2 to 1. For numerical mean and variance, we have added a Cauchy noise scale to the smooth sensitivity to achieve epsilon differential privacy. And also, since the categorical count essentially will change by at most 1 regardless of the category changes or not, the smooth sensitivity doesn't really benefit here, and the Laplace noise is optimal in this case. Okay, we finally do some experiments on the UCI datasets, including adult dataset, mushroom, skin, seed, and glass. We have also tested our algorithm on 9040 census dataset, which is a sample drawn uniformly at random from the US population from the 9040 census. We have built the classifier for 4 different states, including the state of Washington, Oregon, Wyoming, and Nevada. And as a baseline comparison, we have compared our algorithm with the most frequent class, the non-private naive Bayes classifier, the differentially private naive Bayes classifier using global sensitivity by Vadia et al., and as noted by the reviewers with Bonnen-Steinke's mean estimation algorithm. Okay, so here you can see our results. On the left-hand side, you see the results for the adult dataset, which on the x-axis, we have reported the different values for epsilon, and on the y-axis, we have reported the accuracy percentage of the model. In our paper, we have provided approximate DP2, which you can see our results in the figure. So the solid lines are our results, and the dashed lines are the other methods. So on the left, you can see the result for the adult dataset. On the right, you can see the seed dataset. And here on the left side, you see the result for the glass dataset. And on the right side, you see the result for the skin dataset. So this is the 1940s census, which is a kind of larger data set. As you can see, our results are on most of the data sets follow the same pattern. So on the left, we have this result for the state of Washington, and on the right, you see the result for the state of Wyoming. Again, on the left side, we have reported the accuracy percentage for the state of Nevada, and on the right, we have shown our results for the state of Oregon. All right, thank you so much for your time.